Okay, good morning, students. Good morning, students. In the previous class, we have discussed about pulse code modulation, right? Good morning, students. In the previous class, I have discussed about pulse code modulation. Now, today's class, we are going to discuss matched filter, intersymbol interference, and Nyquist criterion for pulse shaping. Okay. Actually, digital communication, what is the data we are going to transmit? The digital communication, we are going to transmit either 1 or 0, right? It is the data we are going to transmit. When we cause error, when we are going to transmit 0 instead of 1, then we can say that that is an error. Suppose when we are going to transmit 1 instead of 0, then we say that it can be cause an error. So what do you mean by matched filter? Matched filter means nothing but it is a filter which is used for optimum detection of the transmitted pulses. It's used for optimum detection of transmitted pulses. See, let the input signal x of t having g of t plus w of t, where g of t is normal input binary signal like ones, zeros, 1, 0, 0, which is affected by white noise W of t, which is applied to the filter, which is linear invariant filter, nothing but a matched filter. It is going to sample each bit intervals for a duration of TB. Is the use of matched filter. What is that? Matched filter, it is a device which is used for optimum detection of transmitted pulses. The input signal we are going to assume as let x of t equals g of t plus w of t, okay, which is find over a finite time interval t, where g of t is nothing but the transmitted pulse which is having a binary sequence of data, ones or zeros. W of t is a additive white Gaussian noise which is having a power spectral density which is of n0 by 2. Okay, then what is the matched filter output? Simply, the output of matched filter is convolution of input signal with its impulse response. That is, y of t equals x of t times convolve with h of t. Okay, we know that the x of t, the input signal, which is g of t plus w of t, where w of t is nothing but noise, where for simplification we are assuming the noise as n of t. Okay, G naught of t is nothing but the response of the signal. N naught of t is response of the noise W of t. Finally, the matched filter, which is having an impulse response and also capable of minimizing the signal to noise ratio by the factor. What is that factor? Which is eta equals g naught of t whole square by expectation of n square of t. What is g naught of t? Nothing but the transmitted signal we are going to receive, which is consists of binary zeros and ones. What is n square of t? The noise signal we are going to find the expectation are nothing but the complete average of the noise signal, which is n square of t. Okay, see the transmitted signal, which is g of t, which is affected by noise, which is applied as input to the noise, input to the matched filter. Then we are going to perform sampling. Then we are getting the output as y of t. Okay. See, the optimum impulse response is given as h suffix opt of t. So the name matched filter. Okay, the name as matched filter. Okay, now let us see what are the properties of matched filter in this class. What are the main properties of matched filter? See, the properties of mainly it should be having three properties of matched filter. We are going to see what are those properties of the matched filter. We'll see the three important properties of matched filter along with its proof. Let us see the properties. Okay. See, first we'll define what is meant by matched filter. Whenever the noise is additive white Gaussian noise, then the optimum filter we call that as matched filter. For white Gaussian noise, we know that the power spectral density is given by S suffix Ni of f, which is N0 by 2. Then what is the impulse response? Or we can say, to find the impulse response, first we'll find the transfer function of the filter, which is transfer function is nothing but the ratio of output to input signal, right? The ratio of output to input, which is k times into x star of f by Sni of f, where Sni of f is power spectral density, which is N0 by 2. Then h of f is transfer function of matched filter. What is x of f? Nothing but the transmitted pulse. So transfer function of matched filter is h of f equals k times x star of f by N0 by 2 e power minus a 2 pi ft. Finally, on simplification, we write the transfer function of matched filter as 2k by N0 into x star of f e power minus a 2 pi ft. So this is the final expression. H of f equals 2k by N0 because we know the relation x conjugate f equals x of minus f. So that should be replacing with, so 2k by N0 x of minus f into e power minus a 2 pi ft. Then how do you obtain the impulse response of matched filter? Simply by taking inverse Fourier transform to the its transfer function h of f. That is simply h of t equals inverse Fourier transform of h of f, that is ift of this thing. So finally we are getting h of t equals 2k by N0 into x of t minus t. Here we are applying the time shifting property. Fourier transform of x of minus t is x of f. Similarly, Fourier transform of x of t minus t shifted by t samples in time domain leads to shifting by f samples in the frequency domain. So based on that, we are writing h of t equals 2k by N0 into x of t minus t. So because we will be having 2 bits of data, ones are zeros, so x of t equals x1 of t minus x2 of t. Then we write the final expression for impulse response of matched filter is h of t equals 2k by N0 into x1 of t minus t minus x2 of t minus t. Okay, this is about the matched filter. What is meant by matched filter? Whenever the noise is white Gaussian noise, we can say that optimum filter is called as matched filter. It is suffered by white Gaussian noise having power spectral density N0 by 2. The impulse response of the matched filter, which is given by h of t equals 2k by N0 into x of t minus t. Okay, this is the formula. Then what is the probability of error of matched filter? See, what is that expression for probability of error of matched filter? This is the function. The probability of error of matched filter is 1 by 2 error function root of e by N0, where N0 is noise, e is the energy of the signal. This is the expression for probability of error of matched filter. Okay, mainly. Now we'll see what are the properties of matched filter. Mainly it is having 3 properties of the matched filter. What are those? First one, the signal to noise ratio. What is meant by signal to noise ratio? Which is nothing but the ratio of signal power to noise power. We call it as signal to noise ratio. It is a parameter to check the performance of communication system, whether it is functioning properly or not. Both signal to noise ratio as well as probability of error, those are the parameters for checking the performance of a communication system. See, the signal to noise ratio of matched filter depends on the ratio of signal energy as well as power spectral density of white noise. That is the first property. Then another thing, the maximum signal component occurs at the sampling instance t equal to t, having the magnitude as E, where E is energy of the signal. Similarly, the output signal of matched filter, which is proportional to shifted version of autocorrelation function of the input signal. See, we prove the first property. What is that? Show that the maximum signal to noise ratio of matched filter is 2E by N naught. We said, right? What is the first property? The ratio of signal energy to power spectral density of white noise. See, E means signal energy to white noise. See, consider signal to noise power ratio of optimum filter, which is rho max equals integral minus infinity. So signal power, that is x of f by noise power. Then power spectral density of white noise, we know, right, which is N naught by 2, where N naught is maximum amplitude. Okay, so rho max equals integral minus infinity x of f. On replacing power spectral density of white noise with N naught by 2, what we get? 2 by N naught integral minus infinity x of f whole square. And we know, right, from the Rayleigh's power energy theorem, integral of x of f whole square, which equals integral of minus infinity x square of t, which is nothing but integration in frequency domain, which is equal to the energy of the signal. So based on that relation, we are replacing this one as rho max equals 2 by N naught, 2 by N naught, and this thing we are replacing with E, 2 by N naught into E. Okay, so simply we write rho max equals 2E by N naught. Okay, so we are simplifying this expression as rho max equals E by N naught by 2. What is E? Nothing but energy of the transmitted signal x of t. N naught by t is nothing but power spectral density of white noise. So simply rho max equals energy of the signal x of t by power spectral density of white noise. Okay, that is the first property, right? The matched filter, it will be depending on the ratio of energy of the signal to power spectral density. Okay, then we go for the second property. What is that second property? So that for a matched filter, the maximum signal component occurs at t equal to capital T. That is because the time duration of a bit. So if you are going to transmit 0 or 0, 1, 0, what is the bit duration? It should be 0 to t. Okay, it should be 2t like that. Okay, it should be bit duration. So starting from 0, t, then 2t like this. The complete samples will be bit duration. Zero, 0t, 2t like that. We call this as complete bit duration. This one as bit duration. This complete is nothing but bit duration. Okay. Now see, show that for a matched filter, the maximum signal component occurs at t equal to capital T, having magnitude as energy, that is energy of the signal x of t. So we know, right, the Fourier transform of output signal for a given input signal x naught of t is nothing but x naught of f equals x of f into h of f, where x of f is nothing but the Fourier transform of the input signal x of t, where h of f is transfer function of the matched filter. We know, right, just now we have seen the transfer function of matched filter h of f. Just now in the starting we have seen the transfer function of the matched filter h of f as well as impulse response of the matched filter, right? So based on that relation, we are writing here the transfer function of magic filter is 2k by n naught into x conjugate of f into e power minus a 2 pi ft. Okay, so simply we are going to substitute this transfer function in the x naught of f. So x naught of f equals x of f into h of f. So x naught of f equals 2k by n naught x of f into x star of f e power minus a 2 pi ft. We know, right? Input and its conjugate give rise to a, it's a total squared power. So that's why x of f into x conjugate f equals mod x of f whole square. So we are replacing with that, then the equation becomes x naught of f equals 2k by n naught on replacing this with mod of x of f whole square into e power minus a 2 pi ft. Okay, then write the expression for x naught of t from the inverse Fourier transform expression. What is that inverse Fourier transform? In continuous domain, which is x naught of t equals integral minus infinity x naught of f into e power plus j2 pi ft df, which is from the definition of inverse Fourier transform. Simply we are substituting x naught of f with this above equation. So that is integral minus infinity 2k by n naught into x of f whole square e power minus a 2 pi ft into e power plus a 2 pi ft df. Okay, then 2k by n naught, because it is a constant, taking outside the integral minus infinity x of f whole square, taking e power j 2 pi f as common. So it will be replacing with p minus t into df. So because the bit is there for duration of t seconds, either 0 to t, t to 2t, or 2t to 3t. The bit duration is total t seconds. So that's why at t equals t seconds, then x naught of t will be write as, so x naught of t equals 2k by n naught e power j 2 pi f, where small t replacing with capital T. So we get 2k by n naught integral minus infinity x of f whole square. Okay, so this thing e power 0, which value should be 1. Okay, again we take the Rayleigh energies theorem, that is continuous integral of x of f whole square, which is nothing but average of the energy signal E. So based on that, x naught of t equals 2k by n naught into E. Okay, so if we assume the maximum value of the transmitted signal is occurring when 2k by n naught equal to 1. So that is x naught of t equals E at t equals t. Okay, this is the second property. What is that? For a matched filter, the maximum signal component occurs at t equal to t, having magnitude as energy of the signal x of t. Okay. Then we go for the third property. What is that? Show that the output signal of matched filter is proportional to shifted version of autocorrelation function of the input signal to which it is matched. The output signal of matched filter, which is proportional to shifted version of autocorrelation function. What is meant by autocorrelation? Correlation means it is used to find similarity between the two signals. Autocorrelation means we have to perform correlation between the two same signals. Okay, for that just write the output signal x naught of t. The output signal x naught of t is obtained from the its spectral of t equals integral minus infinity x naught of f into e power j 2 pi ft df. We know, right, what is x naught of f? From the second property, we write here 2k by n naught into x of f whole square e power minus a. So simply we are replacing that expression 2k by n naught x of f whole square e power minus a 2 pi. So tk by n naught integral minus infinity x of f whole square and taking e power minus a 2 pi f as common. then we are obtaining the relation between energy spectral density and the Fourier transform of the output signal x of f. So that is energy spectral density is denoted by psi of f. What is the symbol? Psi of f, which is equal to square of the magnitude of the output signal x of f. So based on that relation, x naught of t equals 2k by n naught integral minus m to infinity. Here, this thing we are replacing with the energy spectral density psi of f into e power j 2 pi f t minus t. Okay, and we know that from the property of the energy spectral density, the autocorrelation function and energy spectral density, they will a Fourier transform pair. That is, the autocorrelation function, the Fourier transform of autocorrelation function is the energy spectral density. That is psi of f. So that is, what is the relation? R of tau equals integral minus infinity psi of f into e power j 2 pi df. Similarly, psi of f equals integral minus infinity R of tau into e power minus j 2 pi f tau d tau. So based on that, x naught of t equals 2k by n naught into this thing, we are replacing with R of t minus t. So based on that, what we are saying, x naught of t is proportional to autocorrelation function of the input signal x of t shifted to the right by the t samples. This is the matched filter and the properties of matched filter. What is that? Matched filter and its properties. What is it by matched filter and what are the properties of matched filter? Okay. So similarly, matched filter for rectangular pulse. If we apply input as rectangular pulse, then the output of matched filter will be a triangular waveform. Why? Because we are going to transmit binary data ones and zeros, which are nothing but in the form of pulses, which are nothing but a rectangular pulses. If we apply input as rectangular pulse to the matched filter, we get the output as a triangular wave. That means the matched filter, it will also act as a integrator circuit. Based on that, we'll say it will also act as a integrator circuit. Okay. That's about matched filter. Now we'll see a problem related to matched filter. See, a polar non-return to zero. What does that mean? Non-return to zero. Non-return to zero means having a both polarities. Okay, where positive pulses and negative pulses will be there. A polar non-return to zero waveform is to be received by a matched filter where binary 1 is represented by a rectangular positive pulse and binary 0 is represented by a rectangular negative pulse. We have to find the impulse response of the matched filter and draw the impulse response or sketch it. What is that? What is the given data? A polar non-return to zero. That is, it is having two polarities. Okay. See, let us assume the x1 of t is represented by positive pulse, x2 of t is represented by a negative pulse. So find the difference of the signal x of t. It is nothing but x of t equals x1 of t minus x2 of t. Why? Because this is positive pulse and the negative pulse. So let us assume x1 of t positive pulse having amplitude plus a, negative pulse x2 of t having amplitude minus a. Then after finding the difference, what we get? The input signal x of t equals 2 into a. See, this is the graphical form for input signal x1 of t. It is represented over the bit duration 0 to t having amplitude a. Similarly, x2 of t, it is represented over the bit duration 0 to t having amplitude minus a. Then we have to represent for the complete signal x of t, that is x1 of t minus x2 of t. What is its amplitude? X of t equals 2 times the a. 2 into a for the duration 0 to t seconds. Okay, so x of t equals x1 of t minus x2 of t, that is 0 to t, having amplitude 2a, that's why it is represented. Then what is the time reversal of the signal? Time reversal is nothing but simply the folding version of the input signal. We call that as time reversal property. So x of t is nothing but x of minus t, x of n is nothing but x of minus c. Simply the folded version of the input signal, we call that as time reversal signal. So the time reversal signal x of minus t is simply we are folding to this side. So 0 minus t a and 2a. Okay, then similarly x of t minus t. Why? Because we are going to find impulse response of the matched filter. What is the formula? Small h of t equals 2k by n naught into x of t minus t. That's why first we find the time reversal of the signal x of minus t, then its time shifted signal x of t minus t. So x of t minus t, which is nothing but 0 to t, having amplitude 2a. Okay, so the time reversal of the signal x of t is x of minus t, we have drawn. Now delayed by the minus t, that is x of t minus t, which equals 2a. So finally, what is the impulse response of the matched filter? 2k by n naught into x of t minus t, right? So 2k by n naught x of t minus t. What is the amplitude? Which is 2a. So simply 2a. So which is 4a by n naught into k. This is the diagram for impulse response of the matched filter having bit duration 0 to t, amplitude 4ak by n naught. Okay, that is the impulse response of the matched filter for the any given data. Okay, that is about your matched filter. Then we'll see the another topic, which is what is that? Differential pulse code modulation. What is that? Differential pulse code modulation, shortly called as DPCM. What is that? DPCM or differential pulse code modulation. Because in the previous class we have seen PCM, now we are going to see DPCM. What is that? Differential pulse code modulation. Okay, before that, let us see just. Okay, what is that differential pulse code modulation? As the name says, where the samples of the signal are highly correlated with each other. So if you look at the signal, see, on x-axis we have taken x of nts, which is nothing but continuous in amplitude, discrete in time. On y-axis we have taken the bit levels. See, here the sample is 0, 1, 0. Here the sample is 1, 0, 0. Here the sample is 1, 0, 1. Okay, here this, if you look at observe 1, 1, 0, 1, 1, 0, 1, 1, 0. That means what we are doing? We are taken one continuous signal, splitting into equal samples, and each sample will carry certain amount of information. If you look at this part, what happened? Sorry. If you look at this spot, the same sample, that is 110, 110, the same sample carries the same information in 3 times. We call that as redundancy. So why we are going for DPCM is to reduce the redundancy, and we reduce the cost, we are going for differential pulse code modulation. See, the samples of a signal are highly correlated with each other. This is, any signal does not change fast. Its value from present sample to next sample, the, the value of present sample to the next sample, it will not differing by a larger amount. Okay, because the adjacent samples having the same information with less number of difference. So when samples are coded using normal PCM technique, it will contain redundant information. So we are going to remove that redundant information by the help of DPCM. What is that? DPCM. See, this is the DPCM transmitter part and receiver part. What is that? DPCM transmitter part and receiver part. See, what happened the DPCM at the transmitter and receiver part? Let us see the explanation for DPCM transmitter part as well as receiver part. If the redundancy is reduced, what is the main principle of DPCM means? We are going to reduce the redundant information. So if redundancy is reduced, then overall bitrate will decrease. So if overall bitrate will decrease, the number of bits required to transmit per sample will also be reduced. We call this technique as differential pulse code modulation. What is that? If we reduce the redundancy, overall bitrate will reduce, which in turn reduce the number of bits required to transmit per sample. We call this technique as differential pulse code modulation. Mainly this DPCM, it will be working on the principle of prediction. What is my prediction? Simply assuming, or we are going to estimating, which is nothing but prediction. See here, the value of the present sample, see there is a prediction filter, nothing but the prediction filter just predict the previous sample. See the input signal we are assuming as m of n is given as the input, then the prediction filter assuming the sampled input we call as present sample. From the prediction filter we are assuming the past sample. It is going to compare the present sample with the past sample. Then we are going to find the difference between the present and past sample, which is the help of comparator E of n, which is applied to the quantizer. Then we are going to get the quantized value. Again, this quantized value is applied as input to the prediction filter. Again, it should be compared with the present sample. Then finally, we are going to encoding the data using DPCM. See, we will tell you clearly. Here, the value of present sample, that is sampled input, is predicted from the past sample. The prediction, it may not be exact, but it is very close to the actual sample value. It is very close to the actual sample value. See, the sampled signal here, the sampled signal here is denoted by m of n, and the prediction signal that is obtained from the prediction filter, which is mq of n. Okay, what is the comparator does? It is going to find the difference between the sampled signal as well as the prediction filter output. That is E of n equals m of n minus mq of n. The comparator find the difference between actual sample as well as prediction sample. We call this as error signal. That's why, which is denoted by the symbol E of n. So E of n equals m of n minus mq of n. Okay. Then what happened? This error signal is applied to the quantizer. Then the quantizer output is given to the encoder. Then it will again given as input to the, it will be again given as input to the prediction filter, so that we can get the samples equally at the right time. That is the use of DPCM. Okay, then finally the quantizer output along with the previous prediction, it will be added, and we call this signal as quantized signal, which is mq of n. First, the comparator difference is m of n minus m cap of n, that is E of n. Then the quantized signal we call as mq of n. Okay. So finally, the error input is E of n equals m of n minus m cap of n. Okay. Then quantizer output is mq of n equals E of n plus eq of n. From there, we get the encoded PCM output. Okay. Similarly, we can able to retrieve the DPCM. Here, what is the use of decoder? The decoder first reconstructs the quantized error signal from the incoming binary data. It can able to reconstruct the error signal from the incoming data. That is, incoming data is nothing but the DPCM data. Then the prediction filter output and quantized error signal. That is, the prediction filter output and quantized error signal are going to adding in the summer. With the help of summer, then we are going to get the required input signal. This is the principle of DPCM. So if you do one problem, one example, then you get a clear idea for a DPCM technique. We'll see that DPCM. See, these are the required formulas will be helpful for understanding. Before that, just see those samples. See, what is the given data? The sampled input signal, x of t, and the prediction filter input, x cap of NTS. We are going to find the error signal, nothing but comparator, E of NTS equals x of t minus x cap of NTS, which is given as input to the quantizer. Then the quantizer output is EQ of NTS. To this quantizer output, what we are getting inputs, x cap of NTS plus xq of NTS. Finally, we are getting the DPCM output as in the form of binary data. See, these are the relations. E of NTS equals x of NTS minus x cap of NTS. Sampled signal and prediction filter signal. This is present sample, this is past sample. Then quantizer output, we are given, right, EQ of NTS equals error signal, nothing but x of NTS minus x cap of NTS plus quantizer output, Q of NTS. Then xq of NTS equals x cap of NTS plus EQ of NTS. Okay. We'll see the problem, we'll get a clear idea. See, example of DPCM. Consider the input samples. That is, we are giving the input, right? X of n or simply x of NTS. What are the input samples? 2.1, 2.2, 2.3, 2.6. Explain how encoding and as well as decoding is done in DPCM. Assume the prediction filter is the first order one. So x cap of n equals xq of n minus 1. So first we'll write our input samples, because from the data, first we are giving the input samples, right, which is 2.1, 2.2, 2.3, 2.6, 2.7, 2.8. Then the prediction filter output, we know, right, it should be assumed as x cap of n. Okay, initially at the starting there is no data in the prediction filter, so it should be 0. So initially it is assumed to be 0. Then what is the first step? We are going to find the error signal, that is the comparator output. What is the formula? Error signal is nothing but the input signal and the prediction filter output. So E of n equals x of n minus x cap of n. So simply 2.1 minus 0, which is 2.1. So then what happened? This error signal we are going to apply to the quantizer unit. The quantizer output is EQ of n. What is the quantizer does? It will be rounding off to the nearest integer values. So 2.1 is rounding off to the 2. Then what is the third step? What is the third step? See, till now what we have seen, this one, right? For DPCM, See, first we are going to find the error signal, then quantizer output, then again we have to give an input as the prediction filter, right? So what is xq of n? The final quantizer output xq of n equals x cap of n, x cap of n plus the quantizer output. Because from the diagram, what is the diagram says? What is the block diagram of DPCM? First, we are applying the input sample signal and then the prediction filter as the input. Then we are going to find the error signal E of NTS, which is applied to the quantizer. Then we get the quantizer output. Up to this clear, right? Then again, we are giving the quantizer output along with the prediction filter input. That is EQ of n plus the prediction filter data. So we are getting xq of n. That is nothing but quantization value of the prediction filter output. So that's why xq of n equals x cap of n, that is 0 plus eq of n 2. Okay, again this thing, see what happened? Xq of n will be giving as input to the prediction filter. That's why the prediction filter value is 2. Then again find what is the next sample, that is present sample 2.2. It will be compared with the past sample, that is prediction filter past sample. So 2.2 minus 2, which is 0.2. So quantizer output value 0. So again we are going to add these two. So again here, okay, by doing all the samples, what is that? What is x cap of n? Nothing but the predictor output. What is EQ of n? Nothing but the quantizer output. So from this, what is the transmitted data sequence? Because EQ of n is nothing but the quantizer output, we are giving input to the encoder, this one only. What are the inputs? 2, 0, 0, 1, 0, 0, right? 2, 0, 0, 1, 0, 0. We know, right? These symbols or bits cannot be transmitted directly to the encoder. The encoder will be understanding only the bit data, ones and zeros. That's why they are converted into binary form based on the specified length. So that's why 2 should be represented with binary data 0, 1, 0. 0 means 0, 0, 0. 1 means 0, 0, 1. 0 means 0, 0. So this is the digital data which is applying to the encoder. Then finally, this is the DPCM data. So 0 means no pulse, 1 means a positive pulse. That should be represented. The DPCM digital data. Up to this, what we have done? Transmitter part. Okay, this is the transmitter part. Then decoder. What is the decoder? So this is the transmitted DPCM data. It will be giving as input to the decoder, and there should be adding in the prediction filter. Finally, we have to recover this input samples back. We have to recover the input samples back. See that thing? So what are the input levels? This one only, right? The decoder receives this input data from the DPCM transmitter. 200 100, 200 100. Then again, because it will be having the prediction filter, right? So x cap of n, initially 0 samples. Then what is the formula for xq of n? That is prediction filter output. We know, right? X of n plus x cap of n plus EQ of n, which is 2. Will be again giving us input to the prediction filter. So based on that, what we are getting? 2, 2, 3, 3. So the received signal is 2, 2, 2, 3, 3. Okay, this is the received signal. What is the transmitted signal? The transmitted signal is this one, 2.1, 2.2, 2.3. The transmitted signal is 2.1, 2.2, 2.3, 2.6. See, if it will be rounding off, what will become? 2. This will be rounding off 2. It will be rounding off 2. It will be rounding off because about 2.5, 3, 3, 3, right? So input received signal and transmitted signal both are same with the help of DPCM technique. With the help of DPCM technique. That is the differential pulse code modulation and a small problem. Finally, what is the principle of DPCM means? If the redundancy is reduced, then overall bit rate will decrease. Then number of bits required to transmit one sample will be reduced. We call this digital modulation technique as differential pulse code modulation. What is that? Differential pulse code modulation. Differential pulse code modulation. Okay. Now in this class, we are going to discuss intersymbol interference. Right. What is it by intersymbol interference? Now we'll see that. We'll be discussing intersymbol interference. See, let us see what is it by intersymbol interference. Shortly called as ISI. So first of all, what do you mean by ISI means? Let us see. ISI is nothing but, so suppose the data we are going to transmit is this one, right? Because it is a rectangular pulse having 1, 0, 1. So which is obtained to the, which is passed through the channel. Sorry. Which is passed through the channel. Then we are going to get the data. Then what is meant by ISI means, see, suppose this is the transmitted pulse. Here we are going to get another pulse because the time duration of this pulse is 0 to TB. So without completing this pulse, again the pulse is coming here. So in this part there should be overlapping. We call this as ISI. What is that? ISI, intersymbol interference. So finally, what is meant by ISI means? ISI is, it is a form of distortion of a signal in which one symbol will be interfering with the subsequent symbols. One symbol will be interfering with the subsequent symbols, which is called as ISI, intersymbol interference, shortly. ISI means it is a form of distortion in which one symbol will be interfering with the subsequent symbol. Simply, the spreading of a pulse, see here, this is 1 bit duration. After this one, we are going to get another duration. See, this is 1 bit duration. After this, we are going to acquire another signal. But without completing this, it will be coming here. It will be coming here. We call all this as nothing but intersymbol interference. Nothing but spreading of a pulse beyond its allotted time interval. Pulse spreading beyond its allocated time interval will cause interfering with the neighboring pulses, which is called as intersymbol interference. Now we'll see the block diagram of intersymbol interference. What is its operation? We'll see that. See, in baseband digital communication, the second source of bit error is intersymbol interference, which arises when the communication channel is dispersive in nature. What is that? When communication channel is in dispersive in nature, then we get the intersymbol interference. Then we get the intersymbol interference. So, what is the block diagram of intersymbol interference? Let us see. This is the block diagram of intersymbol interference. See, where the binary data can be, the binary data means nothing but ones and zeros. It will be transmitted using passband or baseband. What is in a passband? Where the binary data modulates some carrier and the modulated carrier is transmitted over to the channel. What is that? The binary data is modulated with the help of some carrier signal which is transmitted over to the channel. So one of the baseband systems for transmission of digital data is using discrete PAM signal. See, what is the operation here?